Good afternoon, everyone. I am Jianqi Zhang. My supervisor is Professor Xu Yang from School of Future Transportation, School of Highway, Chang'an University, China. I will be talking about transformer-based pavement crank tracking with Neural PID controller on bearing-guided routes. I will elaborate on 5 sections: introduction, methodology, results and discussion, conclusion and acknowledgements. Section 1. Introduction. China's road network and the number of airports has reached a large scale in terms of infrastructure. Due to traffic laws and natural environmental factors, road surfaces are prone to various distresses such as cracks, ruts, and potholes. Currently, the repair of these distresses is plagued by low efficiency, low working accuracy, and significant security risks. The long-term operation of such massive transportation infrastructure routes in a substantial demand for inspections and maintenance. Currently, there are 3 main challenges. Firstly, road conditions have a significant impact on traffic. Secondly, it is crucial to improve the lifespan of infrastructure. And thirdly, there is a need to enhance the mechanization and intelligence level of road maintenance. It is imperative to prioritize the improvement of road infrastructure treatment capabilities. Section 2. Methodology. General framework of our proposed scheme for pavement crank tracking on wheel-guided routes. This work first describes related issues of pavement crank tracking systems. Additionally, it is deployed on wheel-guided routes to achieve crank tracking. This section presents the details of our proposed method. This article focuses on 2 key aspects of crank tracking in road environment. Firstly, it addresses the challenge of achieving accurate crank segmentation in pavement scenarios characterized by slender crank and complex background. Secondly, it examines the low tracking efficiency of crank tracking control methods in limited parameters tuning conditions. To address these challenges, a crank tracking framework is proposed that example transformer-based fuel network and Neural PID tracking control algorithm. The feature fusion module employs a unified under the popular transformer to encode and decode crank video images, enabling the fusion of image pixels and the feature level. In order to adaptively choose the tracking controller parameters more quickly, a 3-layer structured neural network is used. A detailed overview of the framework is presented in subsequent sections. Crank segmentation with transformer. The proposed module employs a unified V5 under the popular transformer to encode and decode crank video images, enabling the fusion of image pixels and the feature level. In contrast to the initial iteration of UNO V5, this study presents a novel approach that incorporates a 2-branch convolution neural network backbone. It is designed to extract crank features between video frames from the wheel-guided robot. In the context of fusion utilizing FT modules, the fusion process occurs at 3 distinct stages, facilitating the integration of fused characteristics that comprise both coarse-grained and fine-grained segmentic information. Neural PID control for crank check. From this fake bank propagation neural network non-linearly maps the input, output, and error to the three parameters PP, QI, and QD of the PID controllers. In addition, the BP neural network has 3 neural points for the input layer, 5 neural points for the barrier layer, and 3 neural points for the out layer. The commonly used TAM function is used in the hidden layer, combined with BPMN and PID controller algorithm. The online self-tuning of PID control parameters can be realized, and the optimal pavement crank checking motion control effect can be achieved. From this fig, we design the vision-guided robot. To acquire pavement crank video images in the front view scene of the unmanned wheeled robot, a front-mounted rear-sense D435i camera with a 135-degree field of view and an RGBD perception unit is utilized. The embedded environment includes JetBrains 4.4, PyTorch 1.8, Linux Ubuntu 90.04, and ROS Melodic. Section 3. Results and discussion. Results of crank segmentation. From this fig, it describes the visualization of segmentation result on the S2T crank datasets. Our method effectively generates masks that appropriately cover the target cracks, thanks to the utilization of SA and CA to further enhance the performance. FT modules are integrated to fuse crack features. Our method is capable of generating highly accurate binary masks, making it suitable for various complex scenes. Tracking control. This fig describes the comparison results of control algorithm optimization. Experiments are performed on real roads to verify the performance of road crank check and shown in the table. This average absolute error is used as a performance evaluation index. The unmanned wheeled robot uses the proposed method to compare the results of road crank check error with other control methods. In the case of crank 1, our algorithm achieves smallest average crank check absolute error with a measured value of 4.12 millimeter. Number 4. Conclusion. This article has 4 conclusions. Number 5. Acknowledgements. The study presented in the article was partially supported by the National Key Research and Development Program of China and so on. Thank you for your attention.